All right, let's get started. Okay, we've been, before I get started, I've started grading homework 1. Generally, I'm not going to grade the homeworks the TAs are, but we have an odd number of TAs, so I got caught doing this one. Just some comments on homework 1. When you guys did, not everybody, but when a lot of you did your naive Bayes calculations, you did it in the sort of straightforward, take all the probabilities, take the product, and then multiply it times the prior for the class. That works sometimes, but in most computers, or in most problems, your computer will underflow that probability. Or it can underflow that probability. So almost always you want to take the log of that. So basically that means that you take the log of all the probabilities and then you add them together instead of multiplying them. Generally that will result in better precision and little chance of an underflow. From what I could tell, it still worked on this particular. I was grading the MNIST database, or MNIST data set. So it seemed to work there, even though there was lots of multiplications. But in general, multiplications of a lot of small numbers is a bad thing. And you almost always want a log of that. The other comment I had is just from a grading perspective. Most of you put the stuff on the correct pages of the PDF. Some of you didn't. And remember that we're grading 350 submissions. If you put the stuff on the wrong page, it takes me 10 seconds more to grade that submission for each problem. So, you know, in the end, that's an extra minute per person if you all did it. So it's expensive from our perspective. So if this keeps happening, we'll probably start charging, say, 5 points for putting stuff in the wrong place. It's very frustrating to grade these things just because there's so many of them. And every time it's in the wrong spot, that's very frustrating. The other comment is when we ask for snippets of code, unless you truly can't fit, even if it's shrink down, you know, to half size, unless you really can't fit your little snippet that we ask for on the page that we ask for it, don't reference back into the full dump of the code. That takes us a long time. The code already takes a long time to grade, 30 seconds to a minute per person. And anytime I have to go search for the code, you know, that's an extra 30 seconds. So it's one of these things that will probably in the future, if you have a page where we ask for snippets and you say it's on page 7, page 10, and page 13, instead of providing the snippets, we'll probably dock you points for that. It's just from a grading perspective, it's too difficult to go through these and do the lookup constantly. Even if you tell me exactly where it is, remember, we just have some random PDF. It's not easy to go to page 7, page 11, find the correct code, that sort of thing. You can make these, we can zoom in on the PDFs, so you can make this stuff pretty small. But if it is on the same page and we can zoom in, it's twice as fast than if we have to go look it up in your code. So anyways, I think those were all the major comments on the assignment that I've graded so far. Somebody else is grading the first half of the assignment, so we'll see if he has comments on those later on. Okay, so we've been working on high-dimensional data. High-dimensional data is hard to work with sometimes, but what we've been discussing is that often, even though we might have high-dimensional data, there's a lot of correlation between features. And anytime there's correlation between the features, most likely you're going to be working with a low-dimensional feature, in a lower dimensional feature space than the true high-dimensional number of features you have. That's just a fact from correlations. Basically, every time there's a strong correlation, you're reducing a dimension. And so we've been looking at ways to actually do some analysis so that we can find the lower dimensional data set, get rid of some of the low variance sort of noise from that high dimensional thing, and then rotate it back to view it in the original data, the original feature space. So just going through a review, one of the mechanisms we're going to end up using is called eigenvector decomposition. I don't think I actually used that name last week for some reason, but this is a real common technique. Every linear algebra package for anything major will do this for you. You don't have to write this. You just have to look up the function call. What this does is it takes a symmetric matrix, S, and it extracts the eigenvalues and eigenvectors from that matrix. The eigenvectors are going to be orthogonal to each other. So you're going to end up with basically a bunch of vectors that are right angles to each other. And the eigenvalues will represent the variance along each of the eigenvector directions. So you're going to get a list of variances. This lambda is the eigenvalues. It's a square matrix, but it's just a diagonal with the variances along the thing. By convention, it's ordered, big to small, and all the eigenvectors are unit vectors. Just makes it easier to work with. You can rearrange the matrix and rescale to get that every time. Orthonormal, that means all the vectors are perpendicular to each other, and they're all unit vectors. And so we can take the transpose times the original, and we get the identity matrix. That implies that the U inverse is the same as U transpose. And in a high-dimensional space, you can view anything that's orthonormal as a rotation of that space. So you take all the vectors in that space and you rotate them somehow. It doesn't rescale anything. It doesn't move the translate in any way. It's just a rotation. Let's see. Most people are done, it looks like. All right. All right, so we've been looking at something called principal component analysis. This is another name that I don't think I called it on the last class. But this process of sort of looking at the new space, rotating in the this high dimensional space so that everything is all of the you reduce all the covariances to 0. That's called, and then you extract you project down. That's called principal component analysis. So just as a review to go back through what we're going to do, first of all, PCA only works when you have a 0 mean. So that's the first thing you always want to do is you just want to take the original data, translate it so that it has a 0 mean. If you think about a rotation, if you have a non-zero mean and you have a rotation, if you could rotate it around a point here, that's what you want to do. But if you do a rotation when the mean's over here, it's going to be a big swing around that center point. So that's not what you want. So you want a rotation around the 0 point. We just subtract the mean from the data set. Super easy. The next thing is we apply that rotation to get a covariance of 0 among all the different dimensions. We figure out this U transpose matrix by doing the eigenvalue decomposition of the covariance matrix. So you end up with a new covariance matrix of R that is equal to all of the eigenvectors, these are the eigenvalues, which are going to be the variances of the individual components with a 0 covariance among everything. Okay, so now we're in the new space. We have no covariance. And now what we want to do is we want to get rid of a bunch of the dimensions, basically. And the way we're going to do this is we're going to select the eigenvalues that are the smallest, and we're just going to zero out all of those dimensions. So we basically do a projection down from a d-dimensional space to an, this is a little s, in case that isn't obvious, down to an s-dimensional space. Now, why can we do this? Well, if we're selecting that s based on the size of that variance, if you have a really small variance, you can basically say that the values there are all going to be really small, because we know they're zero mean. A very small variance means that they're all going to be close to zero. So by projecting them down, replacing them with zeros, we get rid of just some noise, but it's a very small amount. So generally, this can actually be a positive thing that we'll see later on. Then we talked about actually looking at how much error on average we're adding. So we're looking at the mean squared error between the projected versus the rotated in this high dimensional space. And that comes out to be just the sum of all the variances that we've dropped. So the sum of the eigenvalues that we ended up zeroing out. Which again, those eigenvalues we chose to be small. That's how we chose them, the small ones. So we're specifically choosing a set of eigenvectors that are small, so the sum of those eigenvectors is going to be small. I think most people caught up on that. I'm going to stay on this page anyways, so I guess it doesn't matter. Okay, so let's see. Then the last step we're going to do is we're going to form a new data set called x hat. This is going to be the projected data set in the original space. So we're going to take everything and rotate it back, move it back to where it was. So this is just going to be, it's going to be u, because we need to do the inverse of u transpose, times pi, that's a vector. And then we got to add the means back in to translate it into the original space. So now we're back in, we've rotated this thing back to the original rotation and translated it back to the original position. So now x and x hat are basically the same thing, except where we have removed some of that noise from the original. And this is, we looked at some graphs the other day where we saw this, once you project it down, a lot of the things that had a little noise get flattened even more. I'm not going to look at that again, or maybe I can. It's not informative. We're going to skip that. But let's look at an example here of PCA. So what we're looking at here is a data set that there's a bunch of materials, and somebody came along and they shined a bunch of light on them, and they recorded how reflective things were. And then what they did is they graphed this first one is just the mean reflectance. Move that down. The first one is just the mean reflectance of all the materials. So that's just the means. Not too interesting, other than the fact that the reds reflect a little bit more than the purples. Then we took the covariance matrix and we graphed the eigenvalues of the covariance matrix after the eigenvalue decomposition. And what you see here is what we'd expect for most data sets is that there is a quick drop of the eigenvalues within the first, say, 10 eigenvectors we quickly are down to almost zero variance for all the rest of the dimensions. And this is exactly why PCA works. We take this original thing, there's lots of correlation among the different measurements, the different features for any given measurement, and most of them can be eliminated just by getting rid of them, projecting them out. So here we actually look at the first three eigenvectors. So this is sort of the things, the principal components that are going to make up our new data set. Once you've zeroed out everything, essentially what we're going to do is we're going to come along, and for each new transform data point, for each x hat, it's going to be a linear combination of these three graphs. So you'll have some positive or negative value that gets determined by the rotation and translation that we did, but you're actually going to have a weight on each of these eigenvectors to form any original x. So basically what you can say is that if we look at these, we can add some, the left one is sort of a line that is kind of linear, that goes from a lot of purple reflection down to a very little red reflection. The second one is sort of this little sine wave that says there's sort of whatever, maybe green, lots of green and very little red. And then the last one is sort of reddish to orangish maybe reflection. And so you can make up all the different types of color reflection just by adding these three things together. Which is kind of how monitors work, if you think about it. Most monitors, we use 3 pixel values, red, green, blue, and we just add them together. So sort of this is what we expect about how our vision system works and how you can come up with colors. We don't really care about this. This is just showing the error that we've kind of, just by eliminating things, so you can see it has a really low error, but okay. The next one is actually fairly interesting. This is a data set where we took a bunch of pictures of, I think they were all female, but just basically a framed view of their face. Where they've been centered. They have slightly different expressions, but fairly neutral expressions. But they've all been sort of nicely framed so that they're kind of overlapping. They all look the same. And what we did is, that was just the pixel values. We took the raw pixels. We did the eigenvalue decomposition. And we see kind of the same pattern where, there was 4,096 pixels when you take all of them, and there's a lot of correlation here. So this first graph shows all 4,000 eigenvalues, so a lot of them are near zero. The right-hand side graph is the same thing, just zoomed into the first 20 eigenvalues, and what you can see is by the time you hit 5 or 6 eigenvalues, you've already dropped quite a bit of the variance. And by the time you hit 10, you've dropped a huge amount of the variance. Let's see how this actually works. So here's an example of the mean image. Let's zoom this out so we can see it all. This is an example of the mean image. So if you take all of the faces in this data set and you just average over all of them, that's what you get out of it. It's a little blurry for a couple reasons. One, faces are slightly different sizes. They're shifted slightly. It's impossible to get them exactly centered, so the edges get a little blurred. People have, different features. Eyes are higher and lower, slightly wider, narrower, that sort of thing. Eyebrows are slightly different positions. And then the interesting thing here is some of the pictures had long hair and some of them had short hair. And so you actually get kind of this halo where you can kind of tell how many people sort of ratio-wise, had long hair versus short hair in this particular data set. Then we come along, and these are the first 16 eigenvectors, the ones with the highest variation. And you can actually sort of kind of interpret these, when they're in images, you can kind of interpret. What you're going to be doing is you're going to be adding all of these, you're going to have weights on all of these pictures, and then you're going to add them all together. So you're going to take the original picture with some weight, eigenvector 1 picture with some weight, add 2, add 3, add 4 with positive and negative weights. And you can kind of see what they're doing here. You have sort of a base face. Then you add in this second one, which is basically saying they have hair or not. Like that's, to my read on it is they're really saying that you have a lot of hair or you don't. The third one is very similar. Now they can get rid of hair or add more hair. By the fourth, you're starting to see these halo patterns of sort of a dark patch and a light patch. That is, if you just think about how the image is formed, if you add a dark patch here and a light patch here, you're basically translating that face just a little bit. So a lot of these things are, if you have a light and dark patch, you're moving things up and down, left and right, doing some sort of translation. And you can see these, as you get down farther into these, you see a lot of these sort of light, dark, light patterns where things are moving around. Lips are moving up and down, chins are moving up and down, sort of thing. So you can kind of interpret these a little bit. You would never do it, actually try to make a face probably by doing this, but actually that would be interesting. See if anybody can come up with their own face by adding a bunch of these together. Here's an example of an actual sample image. So it's an image of one person. The original's there. And then you can see sort of the top row is how many combination of eigenvectors we used, how many principal components we used. And the bottom row is the error that from the original photo. It shows the sort of the difference between the original photo and that recreation that we've made. And so you can see that, with the mean or a single eigenvector, single principal component, they're real similar. Or sorry, they're not really that much similar. There's a lot of error in there. But by the time you get out to say 10 principal components, you're starting to see a person that looks a lot like the photo. And by the time you go to 100, that person is, it's almost the exact same photo. Like you've recreated this with a level of noise, a level of error that is basically just a little bit of noise that visually we probably couldn't tell the difference if you really showed us these two pictures. So the interesting thing here is that we took something that was a 4,096 dimension feature vector, and we've squashed it down to a feature vector of 100 values. So we've got a lot of compression in this sort of feature space to recreate an image fairly accurately. So this is really what we want from principal component analysis, is to find these things in the lower dimensional feature space and be able to recreate them, sometimes for compression purposes, sometimes to reduce noise. Sometimes we'll even, if you have noise in the image or missing values in the image, this will get rid of them or fix them, because individual pixels that have noise in them, this is actually what we're doing for one of our assignments, is we will take the stuff and we'll eliminate those noise from those random pixels that are wrong. I think that's all I wanted here. Okay, cool. Okay, questions so far? Okay. All right, so as we were sort of discussing, Oh, one comment is that we could ask, we talked about the error in this projected space, which was the rotated zero covariance space. We probably want to talk about the error in this x hat space. But it turns out that because we're only doing a rotation, and this is just a distance value, and rotations don't change distances, the error in the original space is the same as the error in the projected space. So the error for this is exactly equal to that, which is a nice thing. We don't have to worry about doing some sort of translation and rescaling of those variances. It just comes back out to be the same, which is good because we chose the projection to minimize the error in that translated rotated space. So we obviously want that error to be representative in the original space. Now we're going to look at a real quick way to think about principal components, and this is actually why we call them principal components. Move these over here. So if we were to line up, if we have our U matrix, we can rewrite this essentially as a bunch of column vectors put together. How many dimensions do we have? We have D dimensions. So we can just concatenate them all together. We're not adding them. We're actually just making a matrix that's this will be D by N by D matrix. And then if we think about any given data point, if we look at this projection, we know what the form of that is. So that is some R1 up to RS, sorry, this is some RI, and then the S component, the first component, and then 0, 0, 0. And so when you multiply a matrix times a vector with a bunch of zeros, you're basically selecting a bunch of columns and adding them together. So if you think about this multiplication, everything from all the vectors from S plus 1 to D get zeroed out. So all we're doing is adding up all of these vectors to find our original our data in the original space. So that means that we can write our x hat as a sum of the principal components. Where did that go? So if we have j principal components where j equals 1 to s, we can talk about some weight, which is the example and the component. I apologize that we changed nomenclature here a little bit. Instead of putting the j up here for component, we write it down there for some reason. Times the eigenvector, the principal component that we're adding. So this is just what I was saying earlier. We take all the principal components and then we add them all together with a weight. And that weight can be positive or negative. That weight's determined just by the way we do the translation. We end up with that weight. And so these are called the principal components, and then these are the weights of each of the principal components. So any x hat is going to be an addition of all the principal components together. So that's kind of the high-level principal component analysis. Are there questions on that? Because now we're going to get to some just sort of other things that have to do with this. Okay, so probably the biggest problem with principal component analysis is going to be that it requires us to calculate the covariance matrix. So if we go back, oh no, it's right here. When we calculate U, we need to have the covariance matrix of X. Now, for a small number of features, 10 features, the covariance matrix is going to have basically 50 unique values because you have to, it's 10 by 10, but they're reflected across the diagonal, so, basically you get 50 values. You get half of the square. So if you think about this, by sort of the law of large numbers, to get a good estimate, you might need, 30 samples. It'll depend a lot on the variance and whatnot, but let's say you need 30 samples for each of the covariances. So now we're going to need, 1,500 data points to maybe get a somewhat decent estimate of that covariance matrix. You might even need more depending on, how much variance there is, how much noise there is in the data set. That's reasonable. 1,500 examples isn't too bad. But if we start talking about high-level or larger things, to get good estimates of those covariances, let's say we take our example where we had 4,096 data points, features. Not data points, features. Now you have 4,096 squared, divided by 2, and then you need 30 per thing maybe. So you need millions of data points to properly estimate the covariance matrix. So the covariance matrix you almost never want to actually calculate. Not only is it extremely expensive to calculate, because now you have to do this big calculation, but it is going to be really high noise to it because you're just not going to have enough data to really calculate each of those covariances with any kind of fidelity. So that's going to be a big problem. So we're going to talk about a method here that gets around having to calculate the covariance matrix. There's actually a bunch of methodologies that will allow you to do this. We're going to talk about one here where if we just want one or two principal components or a low number of principal components, we can calculate those kind of directly. Later on, we're gonna look at techniques that if we need a lot of them, we can do it without calculating the covariance matrix. It'll give you the same stuff. It'll just be much more efficient computationally. Okay, so the technique we're going to talk about is called NIPALS. You can look up in the book what that stands for. I always forget. It's some big acronym. I think it's NIPALS. And NIPALS is going to be an algorithm that will calculate, like I said, just a couple principal components. If you need 100 principal components, it's the wrong thing to use. If you have 5 principal components that you need, it can be computationally efficient to use it. And here's the way that NIPALS works. First, we're going to just assume we have a zero mean data set, just because we don't want to carry around that mean. If we don't have a zero mean data set, we know how to adjust it to be zero mean. We don't really care about that step. So we're going to make that assumption. Now, as we said, x hat. Now, let's assume we only want to find one principal component. If we want to find one principal component, x hat I is going to be the very first eigenvector, or principal component, as we call them, times some weight. So it's always the first principal component, and then it's the weight associated with that for that particular thing. And so this is going to be sort of the lowest fidelity estimate that we can come up with because we're only using one principal component, but it can still be useful. So let's consider a data matrix, which is just all of our data we're going to take our data and remember we always consider our data as column vectors. However, for historical reasons, when we build a data matrix, all the data is rows. So each row is an individual data item, and then the columns are features. That's just the way all statistic books are written. If you don't do this, if you try to do it the other way, you're going to have to translate every single formula you ever see. So almost always things are column vectors, and data matrices are the kind of the exception where the data is aligned sort of along the rows. And then we want to consider a data matrix X hat. Now this is going to be our data matrix that we form by just using this formula right here. For reasons unknown, I swapped the value order here. So we really want that W in the front. This is a scalar in this case, so we don't care. We can move it. But later on, in a second, we're going to want it in the front. So if we think about this, this is the weight associated with data item 1 times the principal component 1. And then we have the second data item, and we're still only looking at principal component 1. So that'll be 1. And this is down to n, principal component 1. And again, the W's are all scalars. We could do a little manipulation, and we end up, we can write this in vector notation as W, I'm a little confused by my notes there, W times U transpose 1. So basically, we're just going to take this is an outer product, so we're just going to take the set of weights, make a vector out of it, and then to get the data matrix, we can just take the outer product of that. And now we want to find, basically what we want to find is this W and this U. So before we found them by doing this eigenvalue decomposition of the covariance matrix. That's too expensive. So we want to find this just for one principal component. So we're going to build up a minimization task where we can find those two things just by doing a minimization. So what we're going to minimize is the difference between x and x hat, because that's going to be the sort of the least amount of error. If you talk about x versus x hat, you take the square of the difference. That's sort of the error, and we want the least amount of error we can have. So in this case, we're going to minimize so this is just the component differences. That F means it's the component differences all added up and squared. And that's the equivalent. So this is basically the square distance between the two. And that we can rewrite as, get my indices right here, a sum of all the individual components so that says data item I and feature J, basically. And we're just going to add those all up. So anytime we want to minimize something, probably the first thing we're going to do is take the derivative and set it equal to 0. David makes a big to-do when he originally taught this class about how anytime somebody says minimize, you guys should say take the derivative and set to 0. That's not always true, but it often is the case that that technique will solve a lot of minimization problems. So we're going to do that. To do that, we need to have, let me just rewrite this slightly. So we're going to minimize, we're going to add a half just so the math works out nicely. It's the summation of I to j, so that's the double summation of the xij minus wi u1. And it's the square of that. And we're going to call that C. And C just stands for cost. It's just what the thing we're going to minimize. Then if we look at the derivative of C with respect to an individual specific W, we end up with this. This is over J minus WK U1 times U1. Oh, no, this is, annoyingly, this is actually UJ. There's some frustration. This is how it's written in the book. Again, we've swapped what that index means. Here, we were using it to mean that it was the first principal component. Unfortunately, here, we're mean that it's the first principal component and the jth feature of it. So we're actually looking at the jth feature of that first principal component, even though we use the same nomenclature. So you got to watch that. The book switches back and forth a little bit. Definitely from chapter to chapter, but even within a chapter, you can get a little burnt by that. Now, why are we only summing over J? The key is that when we're taking the, we would normally have a summation over I out here, but when we're considering the kth component of W, anything where I is not equal to K ends up with a value of 0. Just because if you're taking a derivative with respect to W kth, and it's not, you're going to eliminate all the ones that don't have that component in their expression. So that whole summation ends up dropping. So you end up with a summation over just J of this. We can rewrite this in matrix formation. So if we just do the gradient of C with respect to W, we end up with the data matrix times W times U's transpose. So these are both vectors. Basically, these are all vectors at this point. Those are not vectors. Wait a second. These are not vectors. But that is not a vector. I apologize. This is a problem with switching back and forth on the way that we represent these things. And that should be times U. So that is the gradient with respect to W. We're going to set that equal to 0 in order to do the minimization. We also need to calculate the gradient with respect to U of C. This is going to be very similar, but basically you're going to swap a couple values. And that we're also going to set to 0. We're going to label this equation 1, equation 2. Now, normally when you minimize things, if you look at this, that's going to have a little problem doing the minimization. Because we have two equations, it's a fairly complex expression If you can't really solve for u or w individually, so it's kind of a train wreck here if we do just, we're going to solve for both u and w. However, we do know that if we knew u, let's just say we knew u. If we know u, then the gradient of w, the gradient of c with respect to w is linear in w. So then it's easy to solve. If it's linear in w, we can just do the math to solve that. If we knew w, the same thing is true about u. We can solve the u equation, and it's linear. It gives us a nice easy solution. So we're going to just say, just to encode that, we're going to call them u star, but given some u star, we can solve equation 1, and it comes out to be, sorry, being left-handed is really a problem when the notes are on the right-hand side here, or the left-hand side, sorry. The transpose is here. So that's the solution for the w if we knew u. And similarly, so this is sort of corresponding to equation 1. And similarly, if we knew some w star, we end up with x transpose w star over w star transpose w star is equal to u. So this, given that we know these two things, we actually can build a really nice procedure to come up with u and w. And what we're going to do is we're just going to iteratively improve u and w by swapping the estimates back and forth. So we're going to start with some u star. And that u star, we're probably going to start with a data point, just one of the data points. It doesn't matter which. You'll just sort of arbitrarily choose a data point and set u star to that value. Then you'll calculate a new w. That w will be an estimate based on that original u star. Then we'll fix that w, and we'll calculate the u. So now we get a new u estimate, and we'll just go back and forth. And we'll just repeat this until we get down to, we can measure the error between the data set and the new projected data set pretty easily. So we'll just keep going until that's down to a small enough value that we don't care. So this procedure is called NIPALS. And it's really useful for generating a small number of principal components. The first principal component you get directly through this method. The next principal component you can get by taking the first principal component, and we can just take the x, and we can subtract out the estimate here, and then we get some x2. So we use the first principal component to get this, we take it out, and we get some x2. Then we can use NIPALS on that x2, and that's going to give us the second principal component. And we just keep repeating for however many principal components we want. Okay, questions on this so far? Okay, cool. So there's a couple complications here. The first one is that because we're doing a bunch of multiplications and subtractions or additions, we actually lose numeric precision pretty quickly. And so if you want to calculate 2, 3, 5 principal components, you're probably okay with NIPALS. It'll be more efficient than calculating all of them, and you'll get them with fairly high precision. But each one that you calculate is going to accumulate a little bit of numeric error because you're always doing this, this subtraction. And each time you do that subtraction, you accumulate a little error. and then you do a multiplication of that error, and that error will build up over time. And so for a couple principal components, NIPALS works great. For 50 principal components, the 50th is just going to be random junk. Just because you've accumulated too much error, you can't calculate it anymore. So that's sort of the first, when would you use NIPALS? In the end, if you, typically would not use NIPALS unless you know that doing the other fast thing, which we'll cover next chapter, doesn't work well. You do that, if you do that other thing that we're going to talk about, sometimes even that's too costly. So NIPALS gives you a cheap solution if you only need a couple principal components. The other complication is just a real simple thing. If you consider W and U for any given calculation, you can come up with another W and U that's just been rescaled. So if you just arbitrarily scale W and scale down U, you end up with the exact same thing. We really want to eliminate that. So what we're going to do is each time we calculate U, we're going to rescale things to the unit vector. So you'll get a new U. It's probably going to be incorrectly scaled. It'll be not a unit vector. So you'll just scale it down by some amount or up, depending on how long it is. And then you'll scale the current W by the inverse of that. And that just is going to give us you actually don't even need to rescale the W because you're going to calculate a new W in a second. So you just need to rescale it so you're always a unit vector. And that means that you don't have to worry about this fact that things are sort of arbitrarily scaled. All right, so any questions on that? That's sort of the end of NIPALS and how that works. We got about 20 minutes. Okay, so principal components, you're going to lose some fidelity to the original data. Anytime you do a small number of principal components, you're necessarily dropping some, you're projecting it into a lower level dimension and then rotating it back. Given that you're doing that, you're losing some fidelity, but that may not be a bad thing. You can think of this as sort of you're smoothing the data. You're taking advantage of some of the correlation that's in the data. You're eliminating some of the noise that exists at that high dimension. You're just getting rid of it, and then you're rotating it back into the original feature space. Because you're getting rid of some of that noise, you can think of this as sort of a smoothed version of the original data set. And there's cases where this can actually be an improvement. And we're going to do this in, I think, as assignment 3, or possibly assignment 4. I can't remember which one goes in which order. There's 2 PCA assignments, assignment 3 and 4. And we're going to actually do this with images. Because images, we're going to take images, we're going to assume that there's noise in the image, and then we're going to do PCA in order to eliminate that noise. And it's going to actually work remarkably well. Now we're going to go through a little bit of theory here on why that works. So let's go to a new page. So we want to look at what our xi actually is. So our xi is some vector, and this is some observed value. However, when we observe values, any data point, we can kind of make the assumption that that's not the real data point. If there was some ground truth in the world of that feature value, the observed one often won't be that value. I mean, this isn't always true. You know, if you're observing something like gender, there's probably not a lot of noise in that. But certainly for many features, you're going to have some sort of intrinsic noise where you're not observing the real value. Let's say take a photo for a photo as an example. Any given photo, there's some ground truth out in the world of the physical properties of what you're trying to take a photo of. But when you observe it, you have the camera sort of getting in the way. You have the light source getting in the way. You have all these things where you're not really, there's some sort of noise in the measurement. So what we want to look at is sort of the difference between the ground truth of the world that we can't actually ever know and the thing that we observed. So we're going to write the ground truth as a tilde. And then we're going to assume that we've added some noise to this. So we get this guy. That's going to be the noise, and that's actually a vector of some sort. That's going to be the noise that was added to the ground truth to get the observation. So now if we, so just to label these, this is the true value, and this is the noise, where the true value is what actually exists out in the world somewhere. So if we consider a very specific form of noise, we can actually show that a PCA representation is actually possibly better than a non-PCA representation. Again, we don't know what the true value is, and we don't know what the noise is. We just know that together they add up to the observed value. The noise model we're going to consider is a normal with zero mean and sigma squared variance. So that's going to be our noise model. We're not actually going to know sigma squared. We can kind of make an assumption or a guess on it, but we're not going to actually know what that value is either. So we don't know how much noise it is. We don't know what the original values are. There's a lot of uncertainties, but still we're going to be able to do some interesting stuff. So if we look at the covariance matrix, of our x, this is going to be equal to the covariance matrix of our x tilde, that's a tilde, even if you don't believe me, times our sigma squared identity matrix. And the reason that we can break that apart is that we assume that the noise is independent of the measurement, or sorry, is independent of the true value. You know, the noise is just some stochastic process. The true value is a value that exists out in the world. And the noise applies equally to each of the data points that we observe. So we can break that apart. We can then look at the eigenvalue decomposition. This is what we've been looking at the whole time. We can then break apart these variances, which are, again, they're going to be the variances of the individual components that have been rotated to have zero covariance. So we can look at U, just dropping this equation in right here. We end up with the cov mat plus the noise equals the lambda. So what we've done here, sorry, there's a tilde I missed. Right there's a tilde. Again, we have independence, so the covariant matrix can be split in two. There would be a U transpose U around that, sigma squared I. However, we know that U is orthonormal. The inverse, we can use the inverse just to get rid of them. So we end up being able to decompose this, this set of variances. And we can actually rewrite this as the eigenvalues are equal to a new set of eigenvalues so that's just, we're just going to call this equal to a lambda tilde. So those are going to be the variances of the true real world values, whereas this is the variances of the observed values. So now we can consider sort of how much error we have on the observed values versus the true values out in the world. So that error, we can just take the mean error. We end up with xi minus x tilde I. Yeah, that's right. No, that's not right. Where did the summation go? All right, so that's the summation, or that's the error, the squared error. And that's going to be just equal to d sigma squared. So you're just going to, we know that the error is, there's sigma squared error on each of them, and there's d components. So we're just going to end up getting an error of d sigma squared. Now, if we look at, I'm going to want to keep that there, so I'm going to put this over here. We can look at this, this matrix, which is going to have the eigenvectors, the lambda eigenvectors, is going to be equal to the individual tilde lambda plus the noise. And remember, this will be the biggest eigenvector. It'll go down the diagonal down to some lambda. Sorry, this will be 1 and this will be d. And then it's 0 off diagonal. So that's just how you could break down lambda. So now we can look at the error on the mean error of the principal component estimate minus the true real world error. And this actually becomes the summation of all of these lambda tildes. And again, this just comes back to how we calculate the error, where we're going to project out a bunch of things. We'll project out the lowest lambda values, the lowest eigenvalues of these real-world eigenvalues. So the real question is, if the error of the true values compared to the observed values compared to the true values, how does that differ from the PCA values versus the true values? And basically, if this value, this right here, is less than this, then we actually have a better representation of the true thing by using the PCA created estimate versus the observed estimate. So that's sort of the mechanism. Now, again, we don't know this. We don't know this. We don't know those values. But you can see that we expect this to be very small because we specifically chose these to be small. So we, given that there's enough noise and there's a D of them, we expect the PCA to actually be a better representation of the true real-world values. Any questions on that? Okay, cool. Now, for some reason, I'm way ahead today. I have no idea why, so we're going to get out early by 10 minutes. But if you guys would like, next time I can do 10 extra minutes. It's up to you. Yeah, I'm not sure why I got so far ahead. But homework 3 and 4 is out, in case you guys want to look at them. They're PCA homeworks. I think we have you do NIPALS once. We do image smoothing. They should be easier than the SVM homework, which is due tomorrow night. And they should be a little bit easier than probably the naive Bayes kind of you had to write code homework. So good luck on those, and I will see you guys on Thursday.
Actually, to what extent does the accuracy that we obtain count in the grade?
Oh, none. Unless you have it wrong. Like we give a really wide. There's an argument that if you're using a random data set, your accuracy is going to be with 400 people in the class. You have to go out to like, if you knew the variance, the mean and the variance of that, you have to go out to 3.5 lambda or 3.5 sigma to make sure you were fair to everybody. And that means that you get a range of like 20 points on some of these things. So we actually, the way we figure it is we actually run a bunch of simulations, we do the learning, and then we get this big giant thing. So don't worry. But if you get 20%, I think like the accuracies on the naive Bayes for Gaussian went from like 55 to 85 or something like that. So a big range. And then there was people who got like 25% accuracy, which was just obvious. Now, some of those people did do it wrong. Like they got 55 because there was something wrong with their code, but we can't detect that because it could just be they got randomly bad things. So don't worry about it. I guess that's what it comes down to.
Perfect. Thank you very much. So I have a problem for the homework too. So after you use the validation set to find the lambda and final A and B, so do I have to train all the data again to get the A and B, or just use the final A and B?
For this exercise, probably just use the best A and B that you found.
So I don't have to train all the model again?
Yeah, so in the real world, if you were actually doing this, you would probably retrain the model because it depends on how much data you had. If you have millions of data points and you held aside 10,000, you probably don't care. If you have 1,000 data points and you held aside 100, you probably, by adding those 100 in and retraining, you're going to get a better model. So it's really, from a practical perspective, you often do want to retrain, including that validation set into your training data. But for the homework, don't worry about it. You don't need to do it.
So for the auto-grader, what kind of format do you guys use? So what's
it should be in the homework what the format is. Like it should specifically say what the auto-graders is. I think it's just like you take the test set and you submit like, I think it's just either 0 ones or less than 50, greater than or equal to 50. And I think it's just a file of all the data items. Yeah, it should say, I think they have an example submission or something out there. So, yeah.
For step-by-step procedure for like NIPALS, I just want to check that my understanding is correct. So we first like start with a random U, and then we calculate W based on that formula, and then we like normalize it.
You don't need to normalize W.
Just normalize U.
Yeah, you only need to normalize U.
Okay.
You just need to normalize at some point.
One of them.
Yeah, one or the other, because you're just going to be moving them back and forth. But U is really the one that matters, because principal components, we say, are unit vectors. And if you force that, you can't force W to be a unit vector too. It's only one or the other.
Okay. I see. And then we just calculate U and then normalize it.
And then normalize it and repeat.
Okay.
And you don't even need to, like, this last step, if that's your final step, you probably always want to calculate, you want your final thing to be the calculation of W, since you just renormalized by the size of U. So at the very end, if you rescale U, you have to make sure that you rescale W.
Yeah.
But if you're in the iteration process, you don't need to do that because you're going to throw out that W value immediately anyways. So, so just the very last thing you do is you have to make sure that the W, so.
I see. And for like the minimize error part, so if we're just taking this is trying to minimize the rest. So, like, I feel like this equation, this is the error between the original data and the one that we use for,
the
like,
principal component recreation.
Yes.
Using a single principal component.
Isn't
Yes.
that kind of like a constant though? Like, because the principal component are kind of set.
Well, the principal component is set, but all of those W's are going to be different. So you're basically saying, okay, I get that first principal component, and then I'm going to take the original X, I'm going to take that principal component, and I'm going to find a W so that it's as close as the original X as possible.
Okay.
So we're doing both. We're both finding the principal component and finding that W that makes it as close as the original.
But in theory, when we're deriving this equation, we're actually kind of assuming that U is already like there, and then we're trying to find.
I mean, Well, we're gonna in the end find them both, but it finds the same principal component. This method actually finds the same principal component as the covariance method does. The principal components are set; they are real things that you can calculate, and they calculate whether we use this procedure or we use the eigenvalue. They both come out to be the same thing. So sort of U is real, and for that matter, W is also real. But usually you don't calculate W by itself. You calculate it for multiple principal components. Yeah.
Yeah. Thank you.
Yep. No problem.
So I'm confused by the homework problem, like wordings. It says we are supposed to calculate the accuracy of the current classifier on the validation set.
Yep.
Not the Helgaut set.
Yeah. So you're gonna end up with this is just a naming of things.
Okay.
So we break things up like this. We have our test set that you don't use till the very end. You have the validation set for lambda. You don't use that until you have A and B that are the best you think you're going to get.
Okay, yeah.
And then you have a validation set that you change as you go. You use it both to validate your learning rate if you're trying to tune your learning rate, but also just to give you kind of a view of how well you're learning as you go. And this is the one where we reshuffle it all the time. So every season, what we're calling a season in there, we take this whole thing, we randomize it, and we take a new validation set. And that's just to make sure that we're making good use of our data, but still having some measure of how good we're doing. This is kind of cheating. You shouldn't. You're essentially training on this validation data set as you go. That's a bad thing.
Wait, you were training on the...
Oh, okay. So every season we get a training thing. So for a season we only train on this, and then we validate against this. But the next season, because we shuffle this whole thing, we're going to actually train on this, and then we're going to have some new validation set that's different. But you're doing something technically wrong where you're now, these are data points you actually did already train on. That's a bad thing. The idea is that it's not too bad because your A and B have hopefully, that's an A, trying to be an A, they hopefully have moved enough away from those original data points that it's okay. You've kind of moved around into the space. So it's still cheating, but it's not too bad. But that's kind of, this is the final thing. This is for your 5 lambda values. This validation set is sort of the information as you're actually training.
So this one is the one that has length 50, but it's called a validation set.
Yeah. Yeah. Holdout and validation set is, well, holdout means anytime you chunk it up usually. Validation set usually means it's a holdout set that isn't the test set. So it's just sort of, validation and holdout kind of are the same terminology. And so anytime you talk about a validation set, you have to sort of think about what you're validating with it. Here you're validating lambda. Here you're validating your current AB, possibly your learning rate sort of thing. Okay, cool.
Yeah, just a bunch of questions from the lecture.
Okay.
So, just starting off, just to see if I am understanding what's happening here.
Okay.
Is that you have a feature vector, x, right? And then you normalize it, or you get the zero mean values.
Yep, you translate it over to the zero mean.
And then you multiply it by the transpose of the eigenvector, so this should give you a one-dimensional value, right?
Well, no, that's going to give you, it's still going to be the same dimension. We're never changing dimensions. Okay. This is just a rotation. So you can think of this mean is a vector in space. Okay. Now we've just rotated it somewhere else. But we've rotated it so that when you consider all of the r's together, they have zero covariance, and each of the components have zero covariance, and they have some variance that's along the diagonal.
So if I'm to assume correct, each m is, let's say you have 50 data points with 15 features each. So each m is one of those 50 data points rescaled.
Yes, rescaled.
And then you rotate it, and then you invalidate some of the dimensions. So
yeah, you project them down, so you basically zero out everything.
Okay, so what I'm understanding from this is that you're trying to invalidate the things that have the lower eigenvalues?
Yeah, remember, these are variances.
Okay.
So you sort of consider anything that has a really low variance as basically noise. And you say, well, if it's just noise, we can set it equal to zero. We're basically projecting off that, projecting out that dimension. Because if it's noise, we don't actually want it there. We want to sort of consider it without the noise. So yeah, we sort of just flatten it down into a lower number of dimensions. And if you could think about this is actually where we're doing the big dimension reduction, because all of a sudden all these zeros don't represent a dimension anymore.
Okay.
So we go from some D dimension down to S dimension. And as we saw in sort of these graphs, often the eigenvalues drop very quickly. So you might go, you do like for the faces one, we went from 4,000 dimensions down to 100 dimensions. You know, and that's a huge reduction in dimension.
Does that mean like the ones with the lower eigenvalues are highly correlated with other feature points?
Yeah. Well, in the original, yeah. So in the original space, there's a bunch of correlation. Okay. And once we rotate it, we've rotated it in a way that you can no longer talk about what those dimensions are. Okay. They're just some arbitrary, well, not arbitrary, they're dimensions that are the eigenvectors, but we can't say they correspond to anything in the original data set. They're not along the same feature axis at all, but we do know that they're the least variance ones, so they're most likely to be the noise. Okay. And by this argument with the variance, if we want to make sure that our error between our original data set and the new data set, we know how to calculate that. And if we know that's equal to the variances, and we know all these variances are very small, then we can say that really by eliminating these, we're not adding a lot of error. We're adding a very small amount of error because the sum of a bunch of small numbers is a small number, and we don't care about that.
Okay, yeah, that makes sense. And then you just scale it back to the original.
Yeah, and then you just move it back. So otherwise, it would be in some weird formation.
Okay, so my quick question. So I'm assuming I is each data point you have,
yep.
And then J is the feature?
Yep.
Okay, good. So about NIPALS.
Now this is remember this right here. Mm-hmm. I don't want to write in your book, but this guy right here are the principal components in the it's in the original data set, or in the original component space. But what you're going to do is you're going to add a bunch of these things together to get X. So if you think about how the faces data set, we're going to take all those faces from the different images, different eigenvectors, and we're going to add them, subtract them from the mean to get an original face. So that's where these are called the principal components, and then these are the coefficients that, this particular X corresponds to 0.3 of the first principal component plus 0.7 of the second principal component minus 0.4 of the third. So
each data point, we're recreating it using the principal components.
Yeah, you're using the principal components. And it's just a different way of looking at it. It's no different from what we got from doing this projection and translating back. It's just a different way of sort of writing it so that you see it very clearly that we have 3 principal components and we're adding them together to get back our original data set. So it's just kind of conceptual that's why they're called principal components, and we add a bunch of the principal components to get the original.
Okay, just a quick question. Since we're zeroing out S plus 1 to D, does that mean we have to reorder our features depending on which one has the highest covariance or the eigenvalue?
No. It will. You will end up with. You'll end up when you rotate back into the original feature space. You're going to end up with things that you're going to end up with covariances again, and things won't be along axes anymore. They'll still be because we did some rotation. There will be a bunch of correlation. So we've already eliminated it in the rotated parameter space, feature space rather. And then, so it'll still be eliminated in the, conceptually it's eliminated in the original. We've taken noise out of some of those dimensions, but those dimensions aren't aligned along the features. Okay. But you'll often see like, I don't have a good, so if you did this in sort of this one, what you'd end up is, if you eliminated one of these things, it would end up with basically some projection down to this. So you don't need to, because we rotated, we basically took it, zero mean, rotated, projected it, took it back, we end up with this sort of line where it's now one-dimensional in this particular thing. So yeah, you don't have to do anything else once you get it back to the original.
Okay, and just a couple questions about NIPALS.
Okay.
So we're trying to calculate this without the covariance matrix,
Yeah,
right?
because that's super expensive.
So, quick question is, are the weights